DOE CSGF Fellow Nicholas RIVERA in the field of optical physics at the Massachusetts Institute of Technology.
Hello, everybody. My name is Nick Rivera, and today what I want to talk to you about is our recent work on trying to design new types of lasers based on free electron, relativistic electron gain media. And so this is work that was done in collaboration with another PhD student at MIT, Shahrukh Khan, and two professors, Ido Kamener at the Technion in Israel, and Professor Marin Solyati, my advisor. So what do I mean when I say nanophotonic free-electron lasers? Let's unpack that. So the idea is, let's focus on the middle. I have some optical resonance structure. So you can imagine an electromagnetic waveguide that guides electromagnetic fields. These could be microwave fields, these could be optical fields. We're particularly interested in optical fields for compact lasers based on free electrons because the optical wavelength is on the scale of hundreds of nanometers, which means that the overall laser can also be on the scale of hundreds of nanometers. So you can imagine some kind of optical waveguide or an optical diffraction grating or a periodically structured arrangement of optically refractive materials called a photonic crystal, which behaves a lot like a crystal for electrons and solids that leads to phenomena like band gaps and things like that. So we're interested in a range of structures that can control the flow of electromagnetic fields and structures. So now I take this resonance structure described by its electromagnetic permittivity, epsilon of r, and I send in a beam of particles. So these are electrons, typically. So you can imagine electrons coming out of a gun from an accelerator, like you might use in either a linear accelerator or really for our interest, an electron microscope, like a scanning or transmission electron microscope. And so these electrons are coming in with some initial positions and velocities, and they're going to pass through this resonance structure and start emitting electromagnetic fields into the structure because ultimately they're charges. And if these charges move faster than the velocity of electromagnetic waves in this resonance structure, they will start to emit them. And once they emit them, they can undergo a feedback loop where the fields that they emit rearrange the electrons' trajectories, causing the electrons to emit more, amplifying the very field that they started to emit. And this is called self-amplified spontaneous emission and leads to a laser-like field. And so the net result of electrons coming into this resonance structure is some set of output electromagnetic fields and the particles with new positions and velocities, what I call the output particles. So that's kind of what I mean by nanophotonic free electron lasers. I want to unpack the physical mechanism of this just a little bit more. So the idea of a free electron laser, which has been studied quite a lot in the past, is that it's some resonance structure plus a free electron beam. And the free electron beam, unlike regular lasers, is not only the gain medium, but is also the pump of energy itself. Its kinetic energy is the initial pump. So what I'm plotting here is the logarithm of the power in whatever electromagnetic field mode I'm trying to amplify as a function of the electron's propagation through this resonance structure. And so the electrons that come in, they're typically quite noisy. They're emitted from the electron gun according to shot noise. And so that means that their initial positions are random. And that means that their initial phases in the electromagnetic wave are also random. But once these electrons start to emit and their kinetic energy starts to go to the energy of the electromagnetic field, this starts to change. The electrons start to synchronize and become orderly. And so the mechanism is this. Let's suppose that these electrons are emitting an electromagnetic wave of wavelength lambda. Then this electromagnetic wave, which consists of electric and magnetic fields, will exert Lorentz forces, just classical electromagnetic forces, on these charges and rearrange their trajectories. And the electrons' trajectories will be rearranged such that their positions start to organize according to the wavelength of the field lambda. So the electrons are starting to be spaced out by distance lambda. They're not perfectly spaced out by distance lambda, but they're starting to be. And this leads to more efficient emission because this electron current now has a spatial distribution which overlaps well with the electromagnetic field it's trying to emit, which causes it to emit more strongly. But if it emits more strongly, the electron beam density can be rearranged or modulated more strongly, and this leads to a feedback loop where the electromagnetic field energy grows exponentially until a saturation where the electrons are almost perfectly spaced by the wavelength of the electromagnetic field. So these kinds of principles have been explored quite a lot, particularly in the microwave regime, where they're known as things like traveling wave tubes and klystrons, and also X-ray frequencies, where they're known as free electron lasers, like what you might see at the European X-ray free electron laser or the LINAC coherent light source at Stanford. And So the closest inspiration for our work comes from recent work that was done in the terahertz spectral regime, where people sent electron beams at metallic gratings in scanning electron microscopes to produce light in the terahertz region whose wavelength is on the order of hundreds of microns. And this is done by something called the Smith-Purcell effect, which just refers to the special way that electrons emit radiation when they go above periodic diffraction gradients. Now, interestingly, there's been a lack of work in the infrared, visible, and UV ranges, and part of it makes sense. I mean, we have conventional laser media at these ranges. However, free electron gain media can do things in the infrared and visible that conventional gain media cannot, and that's why we're so interested in this idea. In particular, one place where we're quite interested is that the way an electron laser works is all you need is that the electron beam is moving faster than the phase velocity of light in the electromagnetic medium. So if you have some medium with a refractive index of roughly 3 and the electron moves faster than a third of the speed of light, it can couple to radiation and laze. And a medium that has a refractive index of around 3 is silicon. So we're trying to think about developing lasers in silicon based on free electron gain media, where conventional approaches where you actually use the electrons in silicon rather than external electrons from an electromagnetic beam do not work. And that's a bit of a long story, so I won't go to it, but what I really just want to say is that this allows us to realize lasers in new materials that we can't do by conventional means. So part of the developments of this work that I'm showing you, so in one part is a semi-analytical framework for general free electron lasers in nanophotonic systems. And so by nanophotonic systems, I want to reiterate that I mean electromagnetic systems or optical systems that are structured or inhomogeneous on the scale of the wavelength of the electromagnetic field. So you have media that are varying on the scale of hundreds of nanometers. And so what we want to do to describe, so we want a general laser theory that says, if you know the electromagnetic modes or resonances of the structure, what do the lasing properties, what do the output fields and the initial and the final positions and velocities of the electrons look like? So let's assume that the electromagnetic field is expandable in just a few of the electromagnetic modes of the Maxwell equations. So I'm writing the electromagnetic field as a sum of eigensolutions of the Maxwell equations weighted by envelopes that vary not only in time, but also in the direction z, which is the direction of the electron's propagation. And so if we assume that, and assume that this envelope is varying slowly, in other words, that the gain is happening or the amplification is happening over many optical wavelengths, then I can get a scale separation and coarse graining, which lets me write a wave equation for each mode envelope in terms of the positions and velocities of the electrons with respect to each mode. And so this is the most general analytical semi-analytical framework that can describe a free electron laser. And if you tell me the modes, then I can tell you the lasing solution. So this is quite powerful. However, the other part of this work is a new computational ab initio approach to free electron laser physics, where I don't necessarily assume I know what modes are going to laze. Because in laser physics, this is pretty common. Unless you've already measured the system, you're very likely to not really know what modes laze, and very surprising modes can laze. And the only way to really rectify this is to have a start to finish description of the free electron laser, where you actually consider the positions and velocities of every electron as they move through an electromagnetic structure in time, also simulating the dynamics of the electromagnetic field for a 2D or 3D structure. Now, this problem would be borderline impossible if we weren't working in the regime of optics, where the number of electrons that are actually doing this emission is fairly small. It's on the order of thousands or tens of thousands. And so this problem is still tractable. And so this picture kind of summarizes what I mean by ab initio description. If you tell me the initial positions and velocities of the particles and you tell me the permittivity of the resonant structure, then I will tell you the state of the output particles and the state of the output fields. In other words, I will tell you what lasers. And so we implemented a general code based on a finite difference time domain solver. So we took a finite difference time domain electromagnetic solver, such as an in-house one developed at MIT called MEEP, MIT Electromagnetic Equation Propagation. And this FETD code does the following. If you give it an initial condition for the electromagnetic field, or you give it a set of source currents, then it tells you what the electromagnetic fields are as a function of time. And so in particular, one thing that's in the purview of that code is that you can send in a moving electron, because that represents a source current, and see what kind of electromagnetic field that produces. Now, that's a big part of the problem that we're trying to solve with these free electron lasers, but it misses a crucial element. these finite difference time domain codes tend to think of these sources as fixed, which means that when they emit photons, their trajectories are not changed. But that's a key part of this free electron laser instability. And so we needed to modify a finite difference time domain solver in order to do this. And so this makes it closer to what might be called something like a particle and cell solver, except here, this solver allows us to consider very general dielectric nanostructures and nonlinear materials, and actually even the interaction of free electron lasers with other kind of gain media, such as based on two-level systems. So this is quite a general code that can now deal with free electron lasers due to the work that was done here. And so the benefits of this kind of ab initio approach are manifold. So we can deal with things that the semi-analytic theories have a hard time dealing with. So systems where you don't know which modes can lase, systems where the electron beam is not steady in time, but is instead pulsed, so that we can create pulse lasers with higher intensities. And this gives also exact insights into the nonlinear saturation mechanisms that actually dictate the intensity of the light that comes out. And finally, the kind of dream when you have these new computational frameworks is emergent phenomena that the analytical theories really just couldn't predict in any way, or that you couldn't really predict in any way until you saw the final answer done exactly. And so I wanted to show just one example of the semi-analytical approach and one example of the ab initio approach. So one kind of design that we're looking at both theoretically and experimentally is trying to make the threshold current for this free electron laser very low. And so what do I mean by threshold current? If you send in an electron beam current that's too low, you will not get this amplification effect to happen, because by the time that the photon would start to modulate the trajectories of the electrons, it's already absorbed or lost to radiation in the cavity. So you lose that radiation, which means you need enough current to overcome the electromagnetic losses in the system, and the minimum electron beam current that will do that is called the threshold current. So one thing that nanophotonics or nanostructuring of electromagnetic waves does very well is it allows you to design very small but very high quality factor cavities. And so one kind of example of this is this so-called racetrack resonator. So we have this silicon racetrack on top of a silicon dioxide substrate. And basically what this structure allows you to do is it allows you to have the electron interacting in the close vicinity of a structure for a long length, while also allowing the photon to encircle the structure and not get lost. And this photon in a realistic racetrack resonator structure can persist for about 1 million or more optical cycles, which is to say that its quality factor is on the order of 10 to the 6. Now, in order to understand the lasing dynamics in this system, when we put an electron beam parallel to the straight segment of this racetrack resonator, we need to understand the electromagnetic waves that can propagate in this waveguide portion of the resonator. And so here I'm showing the dispersion relation of different modes in this waveguide calculated through a three-dimensional Maxwell eigensolver. And the intersections of the electron beam line with the dispersion lines of 10 different waveguide modes of the electromagnetic field tell you which modes the electron can couple to. This is called a phase matching condition. These intersections represent points where the electron velocity matches the velocity of the electromagnetic wave. And so you can see there are many modes that we can couple to, so we need a theory that can tell us how much gain is to be expected in each of the modes. So here I show a measure of that gain in each of the modes, which is the so-called threshold current. And so this threshold, and so we can see that this threshold current in amperes varies by order of magnitudes for different modes in the structure for different lengths of the structure, whether it's 50, 100, 250 microns. But we can see that there's this mode here, this mode number 7, that has by far the lowest threshold. Now, why am I telling you this? The thing that's interesting here is that the threshold current associated with this mode is on the order of tens of nanoamperes, when the length of this waveguide is about 250 microns. And the reason that that's interesting is that that threshold current is 4 orders of magnitude lower than any threshold current realized in any other frequency regime, the closest thing being this terahertz free electron laser that I told you about. And what that means is that for the first time, such a concept of free electron laser could actually be realized in an electron microscope, and it could be done in a silicon media too. And so now we're trying to experimentally design this thing. Now, very quickly, I also want to show you just one more example of this, which is a free electron laser based on a high high quality factor resonance in a photonic crystal. So here I'm considering a periodic arrangement of silicon posts atop a silicon dioxide substrate. So same materials as before, but just different arrangement. Now instead of a ring, it's a periodic arrangement of these boxes spaced by about 500 nanometers each. And so I propagate 45,000 electrons, which represents an 100 microampere current over 1,500 optical cycles. And this is done with our ab initio code. So here what I'm showing you is the lasing field that's created for the last 20 or so periods of this grating. And what you can see is that one particular mode is lasing. It's actually a mode associated with a high quality factor optical resonance, and you can see that it's radiating out into the far field. Additionally, what I'm showing you, another thing that comes from the ab initio code, is the velocity of the electrons as a function of their position. So this black line here represents the initial velocity that I gave all 45,000 electrons entering the simulation with. But as they interact with this field, their velocities start to change. Some lose energy and some gain energy. The lost energy represents stimulated emission, while the gained energy represents absorption. And you can see many more electrons are undergoing stimulated emission than absorption, which is a clear signature of this exponential amplification of the electromagnetic field. Finally, what I'm showing here are the positions of the the velocities of the particles as a function of their position. And you can see that the positions are organized according to the period of the grating. It's this bunching that I told you about where the electrons arrange themselves to match the wavelength of the optical field, which here is actually the period of the grating. And so you can see all of these features actually come from the ab initio code. And so that's something I think is very exciting. I think we can design systems that haven't been designed before. I'll just skip this part because I'm out of time, but I want to just mention that in terms of realizations, all the parameters that I presented are quite realizable. The electron beam currents can be realized in Schottky field emission sources and electron microscopes, while the resonators, the racetrack resonator and photonic crystals that I showed, are structures that have already been fabricated before. And the major difficulty is actually really getting the electron to travel parallel for long enough, but there's been some interesting work to this effect that you can see here. And so with that, I just want to conclude. I want to thank all of you for your attention, and I also want to thank the CSGF for supporting this work and giving me a very interesting 4 years where I could explore a wide range of topics independently without worrying about the constraints of funding. And so with that, I'll just leave this slide up, shamelessly advertising some of our earlier work on light matter interactions and free electron sources that you can see. So with that, thank you.